Hello, this is the Science Communicator, and today I have a huge pleasure to talk with Professor William Moerner, an American physical chemist and chemical physicist, currently specializing in research in biophysics and imaging of single molecules. In 2014, William Moerner was awarded the Nobel Prize in chemistry for the development of super-resolved fluorescence microscopy. Good morning, Professor. Thank you so much for joining me today.
Good morning to you. It's a great pleasure.
Your research involves the study of the optical properties of single molecules. And first of all, I would like to ask you, what does it actually mean? I mean, what are those optical properties of single molecules?
Yes, it's a great question. You know, a molecule is a very small object. And if you imagine that you have a glass of water, there's a huge number of molecules in that glass of water on the order of 10 with 23 zeros after it. But being able to go to one molecule is a huge challenge. It's an intellectual and technical challenge. And what we have been able to do using optics, using light, we've been able to show how you can detect one molecule and measure its properties. That is, measure basically details of how it works, what kind of light it emits, how it might be oriented, how bright it is, what color it produces, and things like that. This is the achievement that happened because of my research back in 1989.
Yes, you were awarded the Nobel Prize for the development of super-resolved fluorescence microscopy. So I'm just thinking perhaps some lay people, an average lay person listening to us, would like to know what exactly is fluorescence. And then how does such a microscope work?
Yes, well, there's a lot of interesting details about that, and I'm happy to explain them. So you should go ahead and interrupt me if you want me to explain one thing a little bit more, to keep me from talking too long. So when we do these experiments, we are interested in looking at the nanoscale. And so to put that in context, first of all, if you take one hair on your head, the diameter of that hair is roughly 100 microns, or 100 millionths of a meter in size and width. And the nanoscale, of course, is down in the nanometer regime. Okay, so that's 1,000 times smaller than a millionth. So a nanometer is a billionth of a meter. And so that is the scale, the nanoscale. And in fact, that's approximately the size of the single molecule that we are imaging with lasers. So the nanoscale is incredibly important because inside every cell in our body, which are roughly 10 microns or so in diameter. Okay, remember this micron scale, 100 down to just a few microns. And now 1,000 times tinier than that is the scale of the little machines that work inside the cell, the scale of the size of the width of the DNA, the little devices that make cells live, if you like, and therefore make everything about our life and the lives of other plants or animals on the entire planet work. So we want to be able to observe how things occur inside this object down at this very tiny scale. And so the way we do this is by using the light from individual molecules. So you mentioned wanting to know when I say the light from a molecule, I actually do mean fluorescence. What we do is to pump a molecule with, let's say, a green color of light, and the molecules give back emitted light. That's the fluorescence is the term for this emitted light, which is a longer wavelength. For example, orange or red. Pumping green and getting something out, orange or red, a longer wavelength. And so this property of fluorescence, maybe people don't think about it all the time, but in fact, it's the same thing that occurs when you think of day glow socks or day glow shoelaces. These terms I'm sure may not translate very well, but it's if you're maybe at a dance party and they have a black light or ultraviolet light, and sometimes you see bright lights coming back from the people's clothes and so forth at other colors rather than ultraviolet, that actually is fluorescence. That's the same property that I'm talking about. Certain molecules will emit light when you pump them, and those are the ones that allow us to detect single molecules. Okay, so now we've hit fluorescence, and the other aspect here is we have to be able to detect single molecules, which is in fact difficult. That's why it took many hundreds of years before they could actually be detected. And we do that with very precise optical instruments, lasers, special lenses, and so on. And we do this by essentially setting up a situation where there's a very small number of molecules that are allowed to emit or allowed to produce the light. And in fact, this property that I just described of fluorescence at longer wavelengths from pumping light is incredibly helpful, because we can set up an experiment that only looks at the longer wavelengths, okay, rather than the laser wavelength. That shift makes this possible, so that we don't see the extremely bright laser, but we can look for these individual molecules at longer wavelengths when you're imaging it. So that's a big part of this. Now, you also mentioned the Nobel Prize and this concept called super resolution or super resolved fluorescence microscopy. And that's another bit of the interesting story, really, here. Should I go ahead and continue with that part of the story?
Yes, of course. Please do. Mm-hmm.
Okay. So using molecules that give us light back lets us see structures in cells. And so previously, it was always possible to use these fluorescent little lights, or if you want to think of them as labels or signposts or beacons. Maybe you can think of it even like when you're imagining that a boat is trying to come close to the shore in the dark, and there's a searchlight that's helping them figure out where they are. These lights from these molecules allow you to see things where they are, even down on the nanoscale. But the problem with light microscopy previously was the wavelength of light. The wavelength of light emitted from these kinds of molecules is on the order of, let's say, a half of a micron, 0.5 microns. The wavelength is that big. Remember, I said the structures are nanometer sized, but the wavelength of the light is maybe a half a micron or 500 nanometers. Way too big to see the tiny objects. In fact, a single molecule in a conventional microscope looks like a blob, looks like a big fuzzy ball that appears to be 500 nanometers in size. So this super resolution scheme allows us to overcome that limitation. Light was previously low resolution. Light microscopy was limited by this wavelength, and everything was fundamentally blurry in the microscopes. So seeing structures that are down in the 10 nanometer regime was not possible before super resolution. So super resolution is a method for getting around that, and our way of doing this utilizes these single molecules. Because if they are separated from one another, then I can measure carefully where it is very precisely down to the tens of nanometers, 10 nanometer regime. If it's by itself and another one by itself. And so the idea of overcoming this so-called diffraction limit works this way. Imagine, I have an analogy I want to describe to help you figure out how this works. Suppose it is nighttime and you want to see a tree. So there's a tree here, no leaves on it, but you can't even see the tree because it's nighttime. So in order to see the tree, you could place little animals, okay, called fireflies in English. Maybe you've heard of these firefly sort of little flies that emit light, okay? So if and they blink on and off. The important thing is that they sort of turn on and off. So you can imagine that you could place them on all over the branches of the tree, many little fireflies everywhere on the tree. And now you simply take a movie of what you see. And the movie is blink, 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 blink. All of these little flashes of light, these individual flashes of light can be measured and recorded in the computer. And then you can show all their positions at the same time. And then you see the shape of the branches of the tree. So this is fairly similar to exactly what we do in cells on the nanoscale. We decorate the object of interest with these fluorescent light bulbs, and we let them blink on and off by various mechanisms so that we can measure all their positions in the computer from a movie, multiple frames of a movie, and then show all of them at the same time to show the structure of whatever we're measuring at a given time. So that's basically how it works.
Yes, so you obtain the spectra of single molecules, you measure them, maybe let me ask you, what do these spectra tell you? I mean, what's the major benefit of the single molecule microscopy for scientists?
So those are wonderful questions. So the scheme that I just described, I didn't really need to measure the spectra in detail, because if they were all little red lights, all the same color, that's fine. The idea I described would work fine for all little red lights. Now, if I want to see a second molecule, I want to see a different protein. I don't want to just see protein A. I'd like to also see protein B. So you can place different molecules with a different fluorescent emitter on protein B, and then protein B will show up as a different color in this movie. So measuring the spectra of molecules, which means measuring what color they're emitting, allows you to see different structures at the same time. And we do this essentially with a grating, okay, with these, or a prism. You can think of it like a prism that people have seen. The light from a prism sends colors that are different to different directions, and therefore I can see one set of molecules that might be orange and another set of molecules that might be red, and see their structures at the same time.
It's really amazing. And you mentioned you actually began your research in the 1980s. So it started quite a long time ago. I understand it had to take years to develop this research technique. And well, right now I'm actually really wondering how you and the researchers, scientists collaborating with you actually came up with these innovative techniques.
That's a great question. And the answer, in short, it's the way science works. It's the way science and discovery work. And telling you this, the specifics of this case will explain why that's true. I was working at IBM in San Jose, California, and my job at that time was related to optical storage. So we wanted to store data, digital data, like computer data, ones and zeros, and we wanted to store that in the properties of molecules. And in fact, we were specifically trying to use the color of light to be different bits. So one bit would be one color, another bit, another color, another bit, another color, another bit, another color. So that was an application idea, development research, okay? And the beauty of working at IBM at that time is that I could explore the application from a very fundamental point of view, to ask deep questions about the limits of this idea. And the ultimate limit of that idea was, well, can we do this with one molecule at a time instead of doing it with millions of molecules for each bit, okay? And so no one had detected a single molecule before, so this was a scientific challenge, something that had not been done, but I had the freedom at IBM to pursue that goal to try to detect a single molecule. So we did. That was the 1989 experiment. But then very quickly, we saw wonderful surprises. It's a new regime of science, and if you're allowed to explore science, you may see something that you don't expect. Specifically in this case, we saw that some of them were turning on and off. They were even at liquid helium temperatures, which is where all this started. Some were turning on and off. That was puzzling scientifically, and we had to figure out why it's happening. But it gave us the realization, oh, well, molecules blink, and maybe someday there'll be an application for that blinking. And we didn't know that application at the beginning. We didn't, and this is the way science works. Once something new is discovered, it's published and presented to the world. Other people think about it, try to say, well, what can I do with that? What can I do with these fascinating new behaviors that are observed due to fundamental research? And we observed this later in something called the green fluorescent protein, a very important fluorescent marker for biological systems. We observed blinking, and each of these surprises can lead to potential applications. So working at this interface really between fundamental measurements and possible applications had a lot to do with this whole story.
Yeah, green fluorescent protein. Could you elaborate on that? This is really interesting.
Yes, it is fascinating. The Nobel Prize in 2008 went to three scientists for discovery of the green fluorescent protein. Roger Chen, one of my friends, and Martin Chalfie and Shimamura. And this discovery was coming from a jellyfish. These scientists discovered that a particular jellyfish makes a protein. But this particular protein has this fascinating property that it is automatically fluorescent. I don't have to provide any other components. I don't have to provide any, let's say, metal ions or anything. The cell can just make this protein, and it automatically is one of these special fluorescent molecules. And so that turned out to be a revolution in biological science, because biologists could then study cells, and let's say they wanted to study a special protein that is responsible for some steps of cancer or viruses or anything you might want to learn about. If they tell the cell to also make this protein attached to the unknown protein or the protein of interest, then they can make it light up and be visible in these fluorescence microscopes that look for fluorescence. So that's an important label, which is still being used in many areas of biology and medicine. And it was one that we also used for this super resolved fluorescence microscopy.
What research are you involved in at the moment?
Well, one of the things that we're doing, essentially everything is related to single molecules, because this idea can be applied to many areas of science. In material science, the behavior of plant biology systems, such as machines that are involved in fixing carbon, or medicine, biology, disease. And so we have projects that explore new applications in, let's say, for example, imaging the RNA of the coronavirus, okay, the SARS-CoV-2 virus inside cells. As a cell is being attacked by this virus, we can use these methods to observe the RNA of the virus. And where is it? Where is it in the cell? What kind of clumps is it making? What particular structures is it modifying? And so on. Because when you can look inside, you can ask, do I understand that? Do I not understand that? And discover new things. But in addition to applications, we also are developing new methods, new ways to observe these molecules, specifically some interesting optical tricks that let us measure the Z position, or the axial position of where the molecule is located. And in addition to X and Y, in addition to in a plane finding out where molecules are, we have special optical methods that let us see where they are in the Z direction, just from taking a picture of the light coming from the cell.
And now a little more personal question, because I've read about you. You graduated with degrees in physics, electrical engineering, and mathematics. And then after some years, you wrote in your research to include biological systems and biophysics. At school, you were involved in countless activities. In the Polish language, we call such a person an orchestra man or an orchestra woman. In English, polymath probably is the best word to describe a person like that. And is this something you somehow inherited from your parents or grandparents, or perhaps was somehow awakened through some inspiration or role model?
So it's a good question. Thank you for those comments. I have to say that I inherited from my parents and ancestors and so on a curiosity about the world, and a deep interest in understanding the world. My father had degrees in chemistry and had a lot of experience in electronics when he was in the military, and so I learned from him a lot about electronics and radios, and as a young child played with all of these things in addition to chemical experiments and in a little house in the backyard where I did chemical experiments. But the idea really is I grew up during a time in the 50s when there was a tremendous encouragement for children to learn science and to understand how you can apply science. So I was exposed to a lot of scientific courses and things like that through my parents and schools, and so and mathematics was incredibly exciting to me. So I have to say that I was just blessed with the ability to understand and become excited by all of these things, so when I began to study in college, I started as an engineer, but when you learn about mathematics for engineering and you learn about physics for engineering, I got excited about all of those fields. So I just simply had an insatiable desire for learning about science, and this actually is not so crazy these days, because many interesting problems are at the intersection or at the boundary between one field and another field. So learning a lot about one field can give you tools that can be applied to another field. So, and I'm continuing to be a student. I'm still learning things. We're still in with collaborations, learning about new fields. I never thought I would be studying viruses in cells, for example, and all of these things I just find very enjoyable, and but it's also true that there is a thread through that permeates many sciences. The mathematics that you learn to understand parts of physics also apply to chemistry, also apply to biology, also apply in engineering applications. And so once you learn these basic techniques, you can see the same ideas appearing in other fields, which is, of course, really a fascinating fact about human knowledge.
Did the Nobel Prize change your life a lot?
In some ways, yes, and in some ways, not so much. In the sense of I continue as a professor of chemistry here at Stanford, and do research with my graduate students and postdocs, and teach. And so all of those things basically have been continuing, because there's always more scientific challenges to approach. But at the same time, the Nobel Prize, of course, changed my life in the sense that I was able to travel different places in the world that I hadn't been before, and I've got essentially a bit of a platform for being able to try to explain science to a broader community, and to try to help be sure that the people of the world recognize that science is essential if we want to attack the problems of our planet and our societies. So I'm working to utilize the platform of a laureate to try to help in this way.
Professor Moerner, thank you so much. This has been such an inspiring conversation for me, and a huge pleasure.
Oh, it was a pleasure for me as well. Thank you very much for your wonderful questions.
Thank you so much.